Today we're going to do our first lab called Conservation of Momentum. We always have a problem that's phrased in the form of a question, so our problem today will be, is the law of conservation of momentum valid for the collision of two dynamic carts? I've told you that PI equals PF. We've derived an equation that shows that in an isolated system, a system in which we have no external forces, the total momentum remains constant. But is it really? Okay, experimentally, does the law of conservation of momentum hold? Is it valid for the collision of two carts? There's going to be three sets of variables. I'm not going to walk you through these, but I will give you some hints as we're going through the procedure here, and hopefully it becomes somewhat obvious to you as we walk through the procedure. I will remind you that the manipulated variable, there's only going to be one of them. There is one thing that you change here. Now, there's often more than one way of doing it, but there's only one thing that will ultimately be changed. And in response to that, only one thing will be changed. So you're going to see from trial to trial in this experiment, you're manipulating or you're changing something, and then you're going to find that something else changes because of what you changed. Control variables, well, there's pretty much an infinite number of control variables. I don't expect you to list an infinite number of control variables, but you should list the important ones. Okay, there's usually a couple of really important ones that you really don't want to miss when you're performing an experiment. There's thousands of them if you keep going, right? Somebody might say the temperature of the air. Well, technically, yeah, the temperature of the air should be kept constant from trial to trial. But is that really one of the important ones in this one? No. If you put that, I'm not going to mark it wrong because it's right. Okay, but if you miss something else that's really important, that's when you're going to lose the marks. So I don't expect you to list, 20, 10, 5. Okay? I expect you to list the important ones, okay, the really important ones. And if you happen to list a couple others because you're not sure if you should list them or not, that's fine, okay, as long as you list the important ones. So we'll say usually it's times a couple of the really important ones. And hopefully as you're going through the procedure, you have a little light bulb go off above your head that says, oh, wait a second, if I change this, then that would completely mess everything else up, right? Make a note of that. Okay, with your partners, make a little note of that so you don't forget that later on, all right? That's what we're looking for. What would completely mess everything up? All right, so this is what our apparatus looks like, and then we'll talk about what the procedure is going to look like as we look at the apparatus. First thing you're going to have is our two dynamics carts here. Those dynamics carts can be on a track or not. You know what? I'd probably suggest it's almost easier if you don't have them on a track. So maybe just skip the track. Dynamics cart number 1, dynamics cart number 2. We probably, you know what, never mind. I was going to say they probably should be the same type of cart, but it doesn't really matter. Okay, if you're not using the track, it doesn't matter whether they're the same type of cart or not. In addition to the two dynamics carts, you need a triple beam balance scale. So as soon as I learn to spell triple, we'll be good here. We'll have a triple beam balance scale in order to measure the mass of these. When you measure the mass of each dynamics cart, I want you to record that mass and keep them straight. Okay, if you measure the mass of this one and it's 502 grams, and you measure the mass of this one and it's 408 grams, that's fine, whatever. But if you start halfway through the experiment calling this one mass 2 and this one mass 1, then all bets are off, right? That messes everything up. Okay, if you're naming this one mass 1, all right, that's good. Name it mass 1 throughout the whole experiment and make sure that you recognize exactly what the mass of mass 1 is. Don't get those mixed up. It might even be helpful to take a piece of masking tape and just literally label them mass 1 and mass 2 so that you keep them straight. Make sense? Maybe even snap a photo of it so that later on when you go back to write this up, you can go back at the photo and remind yourself, okay, this was mass 1 and I remember weighing this one and it had a mass of this many grams and so on. So triple beam balance scale in order to measure the mass of each of these carts. In addition to that, you're going to have something that you used last year several times in Physics 20. This is called a motion sensor. That motion sensor will be connected by a cord to this device right here that we call an air link. This air link is kind of the neat thing here. The motion sensor collects data, but it can't do anything with that data on its own. It's the AirLink apparatus that actually sends the data wirelessly via Bluetooth to your phone. And through an app on your phone that you're going to have in just a couple minutes, you're going to determine what the initial velocity is of this cart and what the final velocity of this cart is. What it's going to boil down to is this. You're going to send cart number 1 towards a stationary cart number 2. So cart number 2 will initially be moving at 0 meters per second for each of your trials. Okay, cart number 1 will be moving at a certain velocity. I don't know what it's going to be, but at a different velocity each time towards cart number 2. They're going to stick together. There's Velcro on each of these carts, so you can use the Velcro to cause them to stick together. Just make sure when you take 2 carts, you take one cart with one side of the Velcro and the other cart with the other type of a Velcro, right? So that they'll actually stick together. Make sense? Don't take 2 carts with both with the same side of the Velcro. Send cart number 1 down at a certain velocity. Sorry, let me rephrase that. Send cart number 1 down towards cart number 2 with a certain initial momentum. Let it hit cart number 2, and then see what the resulting final momentum of the 2 combined carts will be. Then, what are you going to do? Do it again. Do it again with a different initial momentum. Send it down with a different initial momentum towards cart number 2. Have it stick to cart number 2. Let's see what the resulting final momentum is now for the combined mass, cart 1 and 2. Just keep repeating that. Okay, ideally about 10 times if you've got enough time and if things are working well. Right? Make some sense? Just a quick little reminder, last year you would have seen this as well, but just a reminder, on this motion sensor, there's 2 settings for the motion sensor. You want to make sure that the little switch on the motion sensor is on this one, the picture of the little cart. Okay, we're measuring the motion of carts, so let's make sure the switch is on that cart. All right, what are you going to see? Well, make sure that when you're on the SparkView app on your phone, and lots of you should, well, most of you should have that SparkView app already from last year. If you don't, we'll get you to download it again. But you should see, when it's connected to Bluetooth, you should see this screen. If you don't see this, then that means you're not connected properly to the Bluetooth. Connecting to the Bluetooth it should be as straightforward as connecting your earbuds or your car stereo or whatever to Bluetooth. Okay, it's literally just turn on your Bluetooth, look for the device. Keep in mind that these devices are all numbered differently, so you want to connect your device, your AirLink, not somebody else's. Make sure you got the right one, right? Click on it, and it should connect it. Then you're going to go into the app, and you should see this screen. When you get to this screen, unlike last year where you would have clicked on position, this year, or at least today, you're going to click on velocity. So click on velocity. When you do that, it should take you to a screen that looks like this. It's a velocity time graph that has no data on it. Now, when you press that green button, it's going to start collecting data. Initially, it's going to collect data that's meaningless, right? Because nothing's moving. That's okay. Press the button, send cart number 1 down with a certain momentum towards cart number 2. Now it should be collecting some relevant data. Okay? And then once it collides with cart number 2, they're both going to go off together. We should continue to collect some relevant data. Make sense? Now, when you've pressed start on this button's going to turn red or orangish. When you want to stop collecting data, press the red button, and it's going to stop collecting the data. You should see, theoretically, a graph that looks like, more or less at least, a graph that looks like this. Where do you think you're going to get the initial velocity from. Good news here, by the way. Okay, in most of the activities we did last year in Physics 20, we had to export data, we had to import it into Google Drive. That's an easier process now, by the way. They've streamlined the app so that makes it an easier process. But it's still not as easy as what we're going to do today, because we don't have to export anything. We're going to read our values of VI and VF directly off of our phone screen today without exporting any data. We're just going to read VI and VF off of it and write down the numbers on a piece of paper. Where do you think you're going to get VI? How am I going to get VI, the initial velocity, from this? Where does the collision take place on this graph? When this line goes straight down, right? The initial velocity of this was about 1.8 meters per second. Right? You can see that the initial velocity was about 1.8. Then the collision happened, and what happened after the collision? Well, everything slowed down. Same momentum, but more mass. So my final velocity, in this case, would be about 0.9 meters per second. Just write those two numbers down. VI for trial 1, 1.8. VF for trial 1, 0.9. Now, the reality is, when you see your graph, it's not going to be quite as tidy as this. Okay, there's going to be points like all over the place like this. This is probably going to go like this, because we turned on the motion sensor via the app before we actually wanted to collect data, right? So there's going to be some irrelevant stuff in the beginning. What you also might find is that this may go downwards like this, because as friction has a chance to act, what happens? Slows down, right? Where do you want to collect the final velocity data and the initial velocity data? Immediately before and immediately after, so that we have an isolated system, as close as possible to an isolated system, so that we don't have a chance for external forces like friction, say, to have a chance to come into play. Okay, so look at just before and just after. You know, when I draw this out on the board, it's perfect, right? When you see it in real life, sometimes it's a little bit harder. If it doesn't look remotely like this, then you should probably just do a new trial. Make sense? If you have a hard time distinguishing where that initial and final velocity is, just do another trial. Now, one little hint, actually, to make it easier to get some good data. These carts are fairly small. The motion sensor sometimes has a little bit of a tough time picking up the carts, finding the carts. So if you can make it bigger, like let's say by, here, I got a box right here. If I put a box on it like this, then the motion sensor is going to have an easier time picking it up, right? Maybe even I just take a piece of cardboard, a piece of corrugated cardboard, and then tape it sticking up like this so that it becomes bigger. If you do that, though, that's absolutely fine. Just make sure you include that in the mass. And if you're going to do that, make sure that you don't take the mass of the cart without the cardboard or the box or the book or whatever it is that you're putting on it to make it bigger. All right. So what are you collecting here? Well, of course, the mass of cart 1 and the mass of cart 2. Make sure you keep those straight so you know which one is which. The initial velocity of cart 1, which is coming off of your graph from your phone, and then the final velocity of both cars. And then again, the initial velocity and the final velocity. You're going to measure the initial and final velocity, but what are we really changing here? What are we really changing here? Not the initial velocity, but rather, I think you said it, Bruce, the initial momentum, right? We're just doing that by increasing or decreasing the velocity, right? Really, you could change the mass every trial if you wanted, and you'd have the exact same effect, but it would just create more data, more cumbersome data. So it's easier just to change the velocity. But really, it's the momentum that we want to change here. All right. Now, this is where the analysis, so far, procedure is pretty straightforward. This is where the analysis becomes a little bit different. You're going to plot a graph of VF, final velocity, as a function of initial velocity, or final velocity versus initial velocity. That graph should, in an ideal world, be a straight line. Of course, you're going to have to draw a line of best fit on Google Sheets in order to get a straight line, because the data points aren't going to be perfect. Then we're going to have to use this to figure out whether momentum is conserved. There's going to be several times this year when you're going to see a graph you've never seen before, and you're going to be tasked with figuring out what the slope means. Like, what does the slope of this graph mean? If I give you a position time graph in physics 20, you know that it's velocity because Mr. Coderre and I told you that. If I give you a velocity time graph, you know it's acceleration because we told you that. But if I give you a VF versus VI graph, what's the slope mean? When I look at a new graph, I don't know what the slope means. I got to figure it out. So how do we figure it out? Okay, this is the method that you're going to use several times this year. Probably 10 or more times this year, including one question on your diploma exam. I guarantee you there's going to be a question on your diploma exam where you have to do the same analysis that we're going to do here today. Probably with a different graph. If you get lucky, it'll be this graph, but probably not. Here's what I want you to do. Write down y equals mx plus b. Why? Well, because this is a straight line graph, and every straight line graph is represented by y equals mx plus b, right? Then what I want you to do is substitute Vf for y, the final velocity for y, because the y-axis is Vf. The word slope for m, I don't want to use m for slope because I might get that mixed up with mass. And substitute V1I for the x-axis because that's what's on the x-axis. The y-intercept will be basically 0 you're going to see when you plot your graph, so we won't worry about that one. We'll just cross that off. So y equals mx plus b becomes Vf is equal to the slope times V1I. Then you're going to come up with an equation that has those two variables in there, Vf and V1I. You're not going to find one on your data sheet. It's going to come from this. M1 V1I plus 0, right? Because the second object is at rest, right? Make sense? Equals M total times Vf. Rearrange this to solve for Vf because the first equation is solve for Vf. I get Vf is equal to M1 over Mt times V1I. Anybody want to take a stab at what the slope would represent right now? If we cross off things that appear in both, I'm left with this. Right? The slope of this graph, Google Sheets is going to give you M1 over mass total. You can calculate that, right? This comes from Sheets, Google Sheets. This comes from you calculating, giving your original data. If those two numbers end up being the same, they should be the same, right? If they end up being the same, then you just verified the law of conservation of momentum because we made an assumption right here that the law of conservation of momentum is valid. If the two numbers end up being equal to each other, then the assumption that we made must be correct. Does that make sense? If we make an assumption and things work out the way that we predict they're going to work out, then the assumption must be correct. And so get this, and then tell me if they're the same. Now, they're probably not going to be exactly the same. You'd expect them to be off by a little bit, right, as they always are with experimental data. So do a percent difference calculation. Percent difference is actual minus theoretical. Over theoretical times 100. Theoretically, the slope should end up being equal to M1 over MT. That's what we should theoretically end up getting. But what does it actually end up being? Hopefully the same. So we're going to say it's the slope minus M1 over MT divided by MT times 100. And our rule of thumb is if the percent difference is less than 10%, That's an arbitrary number, but that's our kind of rule of thumb. If the percent difference is less than 10%, then we're good. We're going to say that the law of conservation of momentum was verified. If it's greater than 10%, then we're going to say, no, it wasn't verified. And that's okay. That's a valid conclusion. If your percent difference is 14%, then a perfectly valid conclusion is, no, the law of conservation of momentum was not verified. Okay? That's what I want you to conclude. Don't say that it was if the percent difference was 38%. Your conclusion, was it verified? How do you know? So yes, the law of conservation of momentum was verified. This is known because, well, then just briefly explain how you determined that it was verified, or no, it wasn't verified, and then we know this because, briefly explain how you know that it wasn't verified. Percent difference was 38%. Hopefully it won't be that high, but sometimes it is. Sources of error, this is not new to any of you, except for possibly Ben. This format might be new, but everybody else's format is the same as you've always had, right? In Science 10, Physics 20, Physics 30. Sources of error, like what could be better? Procedure, materials, apparatus, what could have been better? Avoid human error here, right? Avoid like saying, you know, Thomas didn't do a very good job, so we could replace Thomas with Isaac. Like, don't do that. Don't say that. It's kind of insulting to Thomas because Thomas is trying hard, right? Don't do that, right? Don't say, well, we made a mistake with our calculations. Well, then fix it. If we made a mistake with our calculations, right? So avoid things, human error, things like that. We're talking more things like, you know, friction. How do we reduce friction? You know, and so on, things like that, okay? Make sense? Yep. Usually we say, it depends on how good they are. I don't have a firm number on that, but usually I say if you have two really good ones, that's probably good. But if they're not quite as good, then you probably want to go a little bit more than that. It's kind of a judgment thing, but never want to have less than two. But yeah, if they're really good, then I'd be fine with two.